today we'll be looking at section 2 in chapter 2 on infinite limits and also limits at infinity. Okay, so far we've considered different strategies for evaluating limits. We first looked at looking at the graphs, using the tables on our calculator, direct substitution, piecewise defined functions. We looked at the indeterminate forms and how you could further evaluate those using factoring. And today we're going to look at infinite limits and limits as we go to infinity. So infinite limits often occur near vertical asymptotes. So we're going to take a little bit and consider what a rational function looks like and how these infinite limits exist. Okay, so if we have a rational function, we looked at these back in chapter 1 where we have a numerator and a denominator. And we talked about like where the domain is undefined. So for one like this, the place where the domain would be undefined would be at 1, because when x equals 1, that would make the denominator be 0. So that's where we have a vertical asymptote. So you can see here, this is 1 and 2, so it's marked off with 2 increments for each number there. So we have a vertical asymptote at 1. So as we look at these vertical asymptotes, what happens is as we approach a vertical asymptote, the function itself following it as we go up here is either going to go to infinity or it's going to go to negative infinity. In either case, we would say that the limit does not exist, but I would like for you to tell me that when it does not exist, it's actually going to infinity, because that gives us some information that's important to know as well. And you can see just kind of numerically looking at a table here, if we're approaching 1, so each step of the way we're getting a little bit closer to 1, you can see how these numbers are growing very rapidly. And so here, by the time you get to 1,000,000, this would be where we see that it's going to infinity. If we looked at approaching 1 from the left side, using these numbers that are getting closer and closer to 1 from the left, you can see that these numbers are getting closer and closer to negative infinity. As far as some other terminology, what happens here, we've talked about the fact that it's not defined at 1 and that we have a vertical asymptote there. So our function is not continuous there either. So not only do we have a vertical asymptote, but f of 1 does not exist. So all of that's important. And so what we could say is the limit as x approaches 1 from the right side would be infinity. And if you look at the limit as it approaches from the left side, that's going to be negative infinity. And in either case, these would both be the case that it does not exist. So these limits, anytime you're using the infinity symbol, these are called infinite limits, and it just basically says that it's growing without bounds. So there's no value that it approaches, it just keeps growing and growing and growing, and sometimes that's important to know. Okay, if we have a polynomial function, so a polynomial would be something like f of x equals x squared plus 2x plus 3. These have no vertical asymptotes. So a vertical asymptote only occurs on a rational function, and it only occurs at the 0 of its denominator. So this is something to look for when you're talking about rational functions. So anytime you have like a polynomial over another polynomial, then you need to look for where that denominator is equal to 0, and that's going to give us the location of our vertical asymptote and also the place where we might have these infinite limits. Okay, so this one describes the behavior of our function f at each 0 of the denominator. Use infinity or negative infinity when appropriate. Okay, so if I'm wanting to, first of all, find the zeros of the denominator, okay, so that means I need to factor the denominator. And I would say go ahead and also factor the numerator if it factors as well, because that could be beneficial to us. So looking at this, we've got difference of squares, so x plus 1 and x minus 1. This one is going to be x plus 2 and x minus 1. Okay, we have a set of common factors here. So what happens is this is actually a whole, and this one gives us our vertical asymptote. Okay, so if we're looking at this, okay, we're asked to describe the behavior of our function at each of the zeros of the denominator. So 1 0 of the denominator is our vertical asymptote. And that's going to be, if we set this factor equal to 0, we're going to get -1. So we need to look at figuring out what the behavior is around -1. And we also have this whole, and that's going to be at +1. Again, set that parenthesis equal to 0. Okay, so if I look at the graph on the calculator, so we'll put this in for y1, put a set of parentheses around each part of this. Okay, but if we look at the graph, and this is just kind of a rough sketch, what we're going to see is over here at -1, you don't actually see the vertical asymptote, but just imagine that there is one there. And you'll see that the graph looks something like this, and also something like this. Okay, so what we're concerned about is the behavior here at -1. So what I can say is the limit as x approaches -1 from the left. Okay, so as we're coming into -1 from the left, if I'm following the graph, I'm going down here to -infinity. So that's going to be a does not exist. Okay, if I'm looking at the limit as x approaches -1 from the positive side or from the right side, that means we're going to be approaching -1 following our function, and that's going to take us up here to +infinity. That would again be another does not exist. Okay, so the limit itself, the limit as x goes to -1, that overall limit, looking at both sides, since these two don't equal each other, really our only option there is just to put does not exist, because they're definitely not coming together for us. That takes care of at -1. If we look at the behavior as x goes to 1, okay, so we're going to look at the limit as x goes to 1 of our function. Okay, if you plug 1 into this, what you're going to get is 0 over 0, which is one of our indeterminate forms. We've already factored it up here, and you can see that the x minus 1s actually cancel out. So that was one of the techniques that we looked at in the last section. So we'll look at the limit as x approaches 1 of just that part that's left. Okay, so if I plug 1 in, I'm going to get 3 over 2. So the limit as it approaches 1, it's kind of hard to see, but on your calculator, there is actually an open circle there. It's not going to draw in the open circle, but if you look on your table, you'll see that it's not defined there, but it's getting closer and closer to 3/2 for that value. So that describes the behavior of it. Okay, here's one for you to practice with. Okay, so we're asked to find, again, the behavior of the graph at each of the zeros. So if I'm looking at each of the zeros of the denominator, that means I first need to factor everything out. Okay, so I'm going to have x minus 3 and x minus 1 with that. Okay, so I do, in fact, have a like factor. So I have two places that I have zeros in the denominator. I have, first of all, a vertical asymptote, and that vertical asymptote is going to be at 1. And then I have a whole from my canceled factor here at x equals 3. Okay, so those are the two areas that I need to describe the behavior around. So let's take the vertical asymptote first. I would say look at the graph for that. And if you sketch the graph on your calculator, just remember, always put parentheses, or if you use the boxes, that's fine, but always put parentheses around that when you're entering it in the calculator. We have a vertical asymptote at 1 and the graph looks something like this and this. Okay, so the limit as we approach 1 from the left, that's going to be taking us down here to negative infinity. The limit as we approach 1 from the right is going to take us up here to positive infinity, which means the limit as we go to 1 does not exist. And these are technically does not exist as well, but when you specify infinity or negative infinity, it does give an additional piece of information. And then finally, we want to look at the limit as it goes to the whole. So the whole was at 3. So I'm going to plug that into the reduced function here. Okay, so if I plug 3 into that, I'm going to have 1 over 2. So 1/2 would be the limit as it approaches 3. Okay, so this last one here, if you look at this one, you can certainly pause it and try it. If we look at this, the zeros of the denominator, there's only 1, and it's at -3, okay, because I set that factor equal to 0. I don't have any cancellation, so I don't have any wholes. So I only have one 0 of the denominator that I need to look at. Okay, and so you can put that in your calculator. Again, make sure you group that with parentheses. So we'll go over here to -3, and we should see a vertical asymptote there. So you should see a graph that looks something like this, and then also like this, okay? So because this is a squared term, it behaves a little bit different. So as we're approaching -3 from the left, it goes to negative infinity. And as it approaches -3 from the right, it goes to negative infinity. So the limit as x goes to -3 from both the left would be negative infinity or does not exist. The limit as we go to -3 from the right would be negative infinity or does not exist. And then the limit as x goes to -3 overall would be does not exist because it's going to negative infinity. Okay, so that kind of is the limits, the infinite limits around vertical asymptotes, which is important. The last one is looking at horizontal asymptotes, and which involves looking at the function and seeing what's happening as our x gets really, really large. Okay, and we've talked about horizontal asymptotes back in chapter 1, so if you don't remember that, you might want to go back and review that. I think that was section 1.4. Okay. All right, so I've got a couple things to kind of help us here. If we're taking the limit as x goes to either positive or negative infinity, so that's both 1 and 2 here, of something that looks like this. Okay, so let's say x is going to negative infinity of 3 over x squared. Okay, so what we've got is 3 divided by a really large number in the negative direction. So say 3 divided by -1,000,000 squared. Well, if you have any number and you divide it by a really large number, whether it's in the positive or negative direction, that's going to equal, the limit of that's going to equal 0. Same thing over here if it's going to positive infinity. If I have like 5 over x to the 4th, then the bottom is just outgrowing the top, and so it's going to be equal to 0. If I have one here, if I'm looking at the limit as x goes to negative infinity of, say, 5x to the 4th, okay? Right, the 5 is kind of insignificant, but if I'm putting a really large negative number, so like -1,000,000 to the 4th, then because this is an even power, it gets rid of the negative, but it is still just going to infinity, okay? So it would be a case where it does not exist because it's going to infinity. Now, if I had something like the limit as x goes to negative infinity of 5x to the third, that's going to go to negative infinity, because just think about putting in something like negative 1 million. Well, negative to the third power stays a negative, and so it's going to be negative infinity. Now, over here, if x is going to positive infinity, it's not quite as significant, because as to whether it's a it really kind of just depends on whether the 2 is positive or negative as to which direction this is going to go. But let's say we have something like this, then that's going to be going to infinity. If I had something like the limit as x goes to infinity of negative 2x to the fifth, then that's going to go to negative infinity. So it is really important to understand those 4 rules there. Okay, on all of these, especially polynomials, when you're looking at these, what happens is we really want to focus on the dominant term. Okay, so the dominant term is going to be the term that has the highest power. And there's a process we can go through of dividing by the x to the highest power and so forth. But basically, we're going to look at this and we're going to say the limit as x goes to infinity of this polynomial here. When we get to talking about really large numbers, these 3 terms here don't really matter. The only one that matters is this dominant term. So the limit of this whole thing is basically just the limit as x goes to infinity of the 5x to the third. Okay, we just looked at one like that. We said if we've got 5x to the third, if x is going to infinity, then this whole thing is going to go to infinity. So it would be a does not exist with infinity. Okay, so here's one. If we're looking at this one and we want to take the limit as x goes to infinity on this, we've got negative 4x to the fourth plus 2x to the third plus 3x. Again, these really aren't significant. This is the one that we're going to focus on. So it's equal to the limit as x goes to infinity of negative 4x to the fourth. Okay, so what happens is if I'm looking at this as I go to infinity, so as I'm putting a really large number in, then this would be like negative 4 times infinity. And I really can't plug infinity directly in, but I can kind of see the general behavior. So that's going to go to negative infinity. If I look at the limit as x goes to negative infinity, same idea. It's going to be equivalent to this, but I'm going to have negative 4 times negative infinity, but this is to the fourth power. This was also to the fourth power, but because it was positive, a positive to an even power, this part would stay positive. This would be negative because of the 4 being negative here. This one, the negative to an even power, makes this become positive. So a negative times a positive is again going to go to negative infinity. So both go to negative infinity. Going back to the previous example here, I skipped the part about negative infinity, but let's look at the limit as x goes to negative infinity of this one. Okay, so on one like this, you're basically saying 5 times negative infinity to the third. Well, if I have a negative to the third, that's going to stay negative, so that's going to end up being negative infinity. Okay, so I don't want us doing a lot of calculations with infinity because it's not a particular number, but you do need to get to understand the general behavior of it. You may be asked to describe the end behavior of a function. So basically the end behavior is considering what happens as you go off to either positive infinity or negative infinity. So if you hear that terminology, that's what it's asking for. Okay, so like on this one, give a pair of limit expressions that describe the end behavior of the function. So that's just saying, look at the limit as x goes to positive infinity. Okay, so as x goes to positive infinity, again, these terms are insignificant. We're really just focused on this one. So it'll be equal to the limit as x goes to infinity of 7x to the third. So if I'm plugging a really large number in, cubing it and multiplying it by 7, then that means it's going to go to infinity. If I look at the limit as x goes to negative infinity of, again, the same polynomial. Okay, so same thing. These are insignificant terms. So the limit as x goes to negative infinity of 7x to the third. This one, if I'm putting in a large number in the negative direction and I'm cubing it, it's going to stay negative. So positive times a negative is going to give me a negative infinity. Okay, on this one, this will be a good one to practice with. So pause it and try these. All right, the first one here, the limit as x goes to infinity of p of x. Okay, you want to really focus on which one is the dominant term. So the one with the higher power is your dominant term. So that's going to be the limit as x goes to infinity of negative 4x to the fifth. So negative 4 times a really large number is just going to give me negative infinity. And same thing if I'm looking at the limit as x goes to negative infinity, then I'm going to have the limit as x goes to negative infinity of that dominant term there. Okay, so negative 4, a negative to the fifth is going to stay negative. So two negatives will make a positive, and so we'll have positive infinity for that one. Looking at part B, this is going to end up being my dominant term. So the limit as x goes to positive infinity of the 300x to the sixth is just going to be positive infinity. And the limit as x goes to negative infinity. Okay, on this one, I'm putting a large number in the negative direction, putting something like negative 1,000,000 in here, but it's getting raised to an even power. So if it's getting raised to an even power, that negative is gone. So this is going to go to positive infinity as well. Okay, we talked before about finding horizontal asymptotes when we have rational functions that are of equal power. And that's kind of what this is talking about here with the three cases. You can have cases where if the degree of the numerator is less than the denominator, then your horizontal asymptote is at 0. So what that means is the limit as x goes to either positive infinity or negative infinity would be equal to 0. If they're equal to each other, then it's going to be the ratio of their leading coefficients. So these two numbers here would be the horizontal asymptote, and therefore the limit as it goes to infinity and negative infinity. And then if the degree of the numerator is more than the denominator, then each limit's going to either be infinity or negative infinity, depending on the values in the problem. Okay, so this one you're asked to find your horizontal asymptotes. So if I'm looking at this, I'm going to do the limit as x goes to infinity for 3x to the fourth minus 5x squared plus 2 over 4x to the third plus 2x plus 7. Okay, so basically these are insignificant terms, so I'm really just looking at the limit as x goes to infinity of 3x to the fourth over 4x to the third. Okay, so we just talked about the case when the degree of the numerator, which was m, is greater than the denominator. When that happens, there is no horizontal asymptote. And so all of this is going to be either going to positive or negative infinity. And if I reduce this, I can see that it would be 3/4, and then just the x is all that's left because 3 of the x's would cancel. So if I'm plugging in, and I do need to have my notation limit as x goes to infinity here. So if I'm taking the limit of this term here, then that's just going to positive infinity. Okay, if I look at the limit as it goes to negative infinity, same idea here. It's going to reduce down to this ratio here. So the limit as x goes to negative infinity of 3/4 x is going to be negative infinity. So what happens is we have no horizontal asymptote. Okay, if we look at this one here, okay, same idea. These are really not your dominant terms. So if I look at the limit of this function as it goes to infinity, we're going to be looking at 5x to the third over 4x to the fourth. And I would say go ahead and just simplify this as much as you can. So that would be 5/4 or 5 over 4x. Okay, so the denominator's growing, the numerator's staying the same. So this actually has a limit of 0. So it also has a horizontal asymptote of 0. If I looked at the limit as x goes to negative infinity, it's going to basically be the same thing. It's still going to be 0. So it's still going to be y equals 0. Okay, on this one, if we're looking at this, you've got your two dominant terms here. So I'm going to look at the limit as x goes to infinity of 7x to the third over 3x to the third. Okay, so these x's are growing at the same rate. So basically, we're going to have the limit as x goes to infinity of 7 over 3. So that limit is 7 over 3 because the x's would cancel out. And so our horizontal asymptote would be 7/3. If you did the limit as it went to negative infinity, it's going to be the exact same thing. Okay, so just an application problem here for this. If the total number of downloads in millions of a new app T months after it's released is given by this particular function, we want to find and interpret the limit as t goes to infinity of d of t's. Okay, so if we're looking at the limit as t goes to infinity, so basically this is saying as time goes on, what is happening to this function here? Okay, so the 70 is not significant. And if we simplify this, we're going to have 4 over 5. Okay, so our limit there is 4 over 5 or 0.8. So as far as an interpretation, we'll say that there's approximately 0.8 million, which would be 800,000 downloads per month as time goes on. Okay, so like maybe we see an increase as soon as this particular app comes out, but at some point it kind of levels off. And so the place that it levels off at is about 800,000 downloads per month as, as time goes on. Okay, here you're asked to find your horizontal asymptotes. This is just practice. So for part A, if I take the limit as x goes to infinity, this is going to be simplified down to be 4x to the third over 2x to the fourth. Okay, so my larger degree is in the denominator. So I'm going to have 2 over x. So the denominator's outgrowing the numerator, and so that's going to be 0, and that'll be my horizontal asymptote. For part B, the numerator is going to keep growing. So there we're going to have the limit as x goes to infinity of 5x over 2. Okay, because if I reduce this down, I'm going to have 5x over 2. So this is going to go on to infinity, so I have no horizontal asymptote. Now, if the limit were to go to negative infinity, then that would this would go to negative infinity as well. And then part C, we have equal degrees. So that means we're just looking at the ratio of, so the limit as x goes to infinity of 2x to the third over 4x to the third. And the x to the thirds, they don't really do anything. So we have 2 over 4, and that limit would be 1/2. So when I look at something like this, these become insignificant when x is large enough, and so it's just growing in the ratio of 2 to 4 because these all cancel out. All right, our last example here, a newly released smartphone operating systems gives users an update notice when they download a new app. And so we have this equation here that gives us the percentage P of users that have installed the new update after T days. Okay, so first question, what percentage of users have installed the new update after 15 days? And then again after 25 days. So if we're looking at that, the first thing we want to do is just simply plug in the 15 to this equation. So we're going to have 100 times 15 squared over 15 squared plus 100. And so that's going to give me about 69.2. So about 69.2% of users have installed the new app after T days. And if you want to try 25, then that's going to work the same way. You just plug 25 into it. If we look at the limit as t goes to infinity of this expression here, okay, we can see that this would not be really significant. So basically we're looking at the limit as t goes to infinity of 100t squared over t squared. So that limit is going to be 100. Okay, so that basically tells us that as time goes on, the percentage of users that have downloaded the app is going to approach 100%. So basically everybody that's using the app has downloaded the app. And then the last one here, your vertical asymptotes. This is one I would say factor first. Okay, so we have vertical asymptotes that are going to come from the denominator. So those are going to be 2 and negative 2. Remember, always write them with the x equals. And then the horizontal asymptote, that's where we look at the limit as x goes to infinity. Okay, and so on one like this, we're just looking at the ratio of those leading coefficients. So that's going to be 1. So the horizontal asymptote is going to be 1.